In section 2.2, we're going to be looking at something called bases, or that's plural for basis. And if there's a whole section talking about that, you can probably imagine it is important, and we will be talking about it for the rest of the class. So let's get started by defining what a basis is. So a basis here, I should probably have this in green here. I'm going to underline it. A basis of V is a list of vectors in V that is linearly independent and spans V. Right, so as it says, just a list of vectors, independent, linearly independent, and spans the space. So an example, what are some examples? Well, the list where it's 1 and the nth location of the nth element of the list, or the nth vector, is a basis of n, called the standard basis. So I'm just going to draw that. I know that's a bit confusing. So for example, in F2, let's say we have the plane. Here we just have 1, 0, 0, 1. This is the standard basis for F2. Right, it's two of them. And this is the first vector, second vector. So because it's the first one, there's a 1 in the first component, coordinate. And since this is the second one, we have a 1 in the second coordinate. So for example, for F3, the whole x, y, z, our standard basis would be 1, 0, 0, 0, 1, 0, 0, 0, 1. And why? Well, because these are the unit vectors for each axis. And well, it's a list of vectors in V, and they're all linearly independent, and they span the space, right? So for the F3, 3 vectors would span that space, those 3 vectors. In F2, those 2 vectors. In Fn, will n many vectors. Another example. I guess here's a basis of F2. Here, 1 and 2, 1, 2, and 3, 5. How do we know they're linearly independent? Well, there's no scalar alpha such that alpha times the vector 1, 2 would equal 3, 5. So that's how we know they're linearly independent. And so they're a basis of F2. So just because we have this standard basis here of F2, that doesn't mean there's only one basis. There can be multiple. As you can see up here, this is another basis of F2. In fact, there's infinitely many bases you can choose from, but they all should fill that definition. Another example would be the list 1, 2, negative 4, 7, negative 5, 6. Though that is linearly independent in F3. Oh, but this is not a basis. I was getting confused there. Because this is only a list too, and we're going to go over a theorem that pretty much tells us that the dimension should equal the number of vectors in our basis. But this isn't a basis of F3 because, well, it doesn't span F3. The last example, one a bit more interesting, is the list 1z all the way to z to the m is a basis of p sub m of f that spans all the polynomials of degree m, or that space with scalars f. This next result from the next slide is kind of going to help explain why bases are useful. So we're going to have a criterion basis. So the theorem says a list v1 through vn of vectors in V is a basis of V if and only if every V in V can be uniquely written in the form, or that form, the equation here, where a1 through an are scalars in F. Yeah, so this is an if and only proof. So a biconditional theorem, so we're going to have to prove both directions. Luckily, it's a bit short. So first, we're going to suppose that V1 through Vn is a basis of V. We're going to let V be an element of the vector space. Well, because V1 through Vn spans V, there are scalars A1 through An such that the equation in the theorem holds, such that this equation holds. Right, so we can write this V here. This V right here, like with these, because V1 through Vn spans V. So, to show that the representation is unique, we're going to suppose that we also have scalars C1 to Cn, such that we can also write V as C1 times V1 plus dot 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 all the way to Cn times Vn. In other words, we're saying, hey, there's another way we can write this, right? Because that's how we show uniqueness. We assume there's two and show that they're exactly the same one. So, subtracting the two equations, we'll get V minus V, which is 0. So here, V minus V, that's 0 right here. And then A1 minus C1, the scalars, and then all times V1. So on and so forth, all the way to An minus Cn times Vn. I'm just going to erase this here just so we have, so it doesn't block us. Well, that implies that J minus Cj for every j between 1 and n equals 0. Right, so what does that mean? That means that A1 is equal to C1, A2 is equal to C2, so on and so forth. An is equal to Cn. So again, we assumed there was 2, but it's actually 1, so we just showed uniqueness. Now we're going to prove the other direction. Now we're going to make the assumption that with V and V, that vector can be written uniquely in the form given by the equation in the theorem. So again, we're still going to be using this equation. We're saying that every vector in V can be written uniquely. Well, if that's the case, well then that implies that V1 through Vn spans V. Right, because all the vectors can be written as a linear combination of V1 through Vn. So that's how we get that V1 through Vn spans V. So to show that V1 through Vn is linearly independent, we're going to suppose that they're scalars such that a linear combination is equal to 0. Right? So the uniqueness of the representation implies that A1 is equal to A2 equal to A3 all the way equal to An, but they're all 0. And here where I say the uniqueness of the representation, I mean the uniqueness of the representation of this vector V up here. Right? Because we're just taking V equal to 0, which implies that our scalars A1 through An are 0. So therefore, V1 through Vn is linearly independent and hence is a basis of V. Right, so that proves our theorem for the criterion for a basis. So we have, the basis is pretty much the only definition we're going to be going over this lesson. But we do have several more, I shouldn't say several, but a couple more theorems along with the proofs, but they shouldn't be too hard to follow, especially because I think they're not biconditional. But the next theorem says that every spanning list in a vector space can be reduced to a basis of the vector space. So again, if we have a spanning list, we can just reduce that to a basis of the vector space. And the way we're going to show that is with steps. But first, we're going to suppose V1 through Vn spans V. right? So we want to remove, as it says here, some of the vectors v1 through vn, so that the remaining vectors form a basis of v. We don't know which ones we're going to take out, but we can definitely take some out, or if it's not really a basis. So we're gonna, like I said, we're gonna do a multi-step process, and this is how it's gonna work. We're gonna start with b equal to the list v1 to vn. Right, so b is just that list. That's how we're gonna be referring to that list, as b. So step one, if v1 is equal to 0, well then we're gonna take that vector out of the list, out of b. But if v1 is not 0, well then just leave b unchanged. Don't do anything. Right? So now, what's step j? Well, step j, if vj is in the span of v1 all the way to vj minus 1, well then take that out, right? Because our list will still span the vector space, right? Because vj will just be linearly dependent from all those other vectors. So we can still just take it out. But if vj is not in the span of v1 to vj minus 1, well then leave b unchanged, right? Because we'll probably need that in there to be a basis. Actually, we will need that, not probably, we will. So how many times are we going to do that? Or we're going to stop the process after step n. We're going to get a list b. Well, now this list b spans v because our original list spanned v, and we only discarded only vectors that were already in the span of the previous vectors, right? Because they were the ones we took out were linearly dependent, so we just took those out. So this list should still span v. So this process ensures that no vector in v is in the span of the previous ones. Therefore, b is linearly independent by the linear dependent lemma we went over last lesson. Hence, b is a basis of v. And so, for example, in F2, when we had the list, actually I don't know if I already have this written down, but if we had the list 1, 2, I actually think I do, but 3, 6, 4, 7, 5, 9, well, we know that we only need 2 vectors to span F2, so we can take 2 of these out. And if you actually follow the process in the theorem, we should be taking this one and this one out. And now these 2 vectors span the space. But let me erase it because I think I may have this. But if not, if you want to jot these down before I erase it, and may not have it. So there it is. We take the vector space F2. If the procedure in the proof is applied, then the second and fourth vectors will be removed. This leaves 1, 2, and 4, 7, which is a basis of F2. That's an example of this proof, or this theorem, I should say. So our next result is a pretty easy corollary. And this theorem says that every finite dimensional vector space has a basis. This proof is pretty much just 1 line or 2 lines. Okay, 3 technically. But by definition, a finite dimensional vector space has a spanning list. And this previous result tells us that each spanning list can be reduced to a basis. Therefore, our theorem holds. Simple proof. And this next slide is going to show that, this next next result, in some sense, is a dual of this theorem up here, right? Which said that every spanning list can be reduced to a basis. Well, now we're going to show that given any linearly independent list, we can adjoin some additional vectors so that the extended list is still linearly independent, but now also spans the space. Right, so this next says that every linearly independent list of vectors in a finite dimensional vector space can be extended to a basis of the vector space. It may be the case that we don't have to add any more vectors, but if we have to, we can. We're going to go ahead and prove this. It's a pretty short proof. We're going to suppose that U1 through Un is linearly independent in a finite dimensional vector space V. Right, so we're going to let W1 through Wn be a basis of V. So U1 through Um is just linearly independent, but it's not a basis. Or not necessarily one. Well, then the list U1 to Um, and then including also W1 to Wn, that spans V. Right, because W1 to Wn already was a basis of V, so it already spanned V. So we're just adding these vectors U1 to Um to the list. And certainly it spans V. Well, now we're going to apply the procedure, right, from the previous slide, from that long proof, to reduce this list to a basis of V. Right, and this produces a basis consisting of vectors U1 to Um and some W's as well, some of these here. So you're just taking some of those out. And now what did we do? We had this linearly independent list, just added some W's, vectors in V, to span the space V, and to be a basis of V, is what we're trying to show. So that's how we can just extend to a basis of a vector space given a linearly independent list in the space. So, an example, in F3, suppose we start with the linearly independent list 2, 3, 4, and 9, 6, 8. Again, those are linearly independent of what already says here, because they're not a scalar multiple of each other. Well, if we take W1, W2, W3 in the proof on the left, sorry, not on the left, above, should have rows above, to be the standard basis of F3. So what's the standard basis? 0, oh sorry, it was standard basis of F3, just a reminder, 1, 0, 0, 0, 1, 0, 0, 0, 1. So if you just apply that procedure, we just add a vector to it, which would be this one here. And now these three vectors are linearly independent, and now we have three that span and is a basis of F3. So now, using the same basic ideas but considerably more advanced tools, this next result of the next slide can be proved. I guess I shouldn't get ahead, but can be proved without the hypothesis that V is finite dimensional. But we'll see that right now. But as an application of this result, we're going to show next that every subspace of a finite dimensional vector space can be paired with another subspace to form a direct sum of the whole space. Right, so that's the juicy theorem of this section. So the theorem says, suppose V is finite dimensional And like I said from the last slide, we can do this, we can prove this without assuming that V is finite dimensional. But in this case, well, we're just going to assume that V is finite dimensional and that U is a subspace of V. Well, then there is a subspace W of V such that V is equal to the direct sum of U and W. Now this proof is a bit lengthy, shouldn't be too hard to follow though. So, because V is finite dimensional, so is U, right? It's just a subspace of V. So there's a basis, U1 to UM of U. Right? U has that basis. Well, U1 to UM is linearly independent, is a linearly independent list of vectors in V. Right? It's a basis of U, they're linearly independent. So it's certainly linearly independent in V. Well, the list can be extended, right, by the previous theorem. This list can be extended to a basis U1 to UM, and then also including W1 to Wn of V. Now, we're going to let W equal the span of these vectors W1 to Wn. So to show that V is the direct sum of U and W, we need only to show that V is equal to their sum, and that the intersection of U and W is only the zero vector. So we're going to prove this first, right here. We're going to suppose V is a vector in V. Well then, because the list U1 to UM and W1 to Wn spans V, well, there certainly exists some scalars A1 to AM and B1 to Bn in F, such that that vector V can be written as that linear combination we show here. Right, because any, well, yeah, I don't need to explain this, but any vector can be written as a linear combination of those vectors since they span V. That's what we're just saying. So in other words, we have V is equal to U plus W, right, where each of these U's, I'm going to use green for U's, we're in U, and the orange for W's. And each of those W's were in W. Well, therefore, V is in U plus W, completing the proof that V is indeed equal to U plus W. Now, we need to show that their intersection is only the zero vector. So to show that's true, suppose V is in their intersection. Well, there exists some scalars, again, such that a linear combination of vectors U1 to UM is equal to V with scalars A1 to AM in F. Same thing with the W's. Scalars B1 to Bn. Sorry, well, linear combination of the vectors W1 to Wn with those scalars B's, the B scalars, are also equal to V because V is in the intersection. Well, then we can subtract those two linear combinations to equal 0, right, since they're equal to each other. And because U1 to UM and W1 to Wn is linearly independent, it implies that those scalars, A1, all the A's and all the B's, have to be 0, right? By definition of linearly independent. Therefore, V is the zero vector, completing the proof that their intersection is only the zero vector. So this is a pretty short section, but it's definitely an important one. Bases are really important in linear algebra. And like I said, we will probably be mentioning, actually, we will be mentioning those till the end of this course.